Hello, and welcome to this video on the topic of orbital motion. There are all kinds of orbital motion out there in space. The Earth and the other 7 planets, along with the dwarf planets, asteroids, comets, and some other objects, are in orbit around the Sun. Similarly, the Moon orbits the Earth about once every 4 weeks, and remember that the 5 planets in the solar system which are further from the Sun than we are also have their own moons. Each of these orbital motions has one thing in common. They're all caused by gravity. The gravitational force which is exerted on the Moon by the Earth is what keeps it in orbit. Another way of saying this is that gravity provides the centripetal force which causes the Moon to circle the Earth. At all points in its motion, the direction of this gravitational force is perpendicular to the Moon's velocity vector. The circular motion of the Moon around the Earth, or of any lower mass astronomical object around a higher mass one, can be compared to a ball being swung around in a horizontal circle by a string, or a car travelling round a bend. For the ball, the tension in the string is what provides the centripetal force that allows it to move round in a circle. For the car, it's the friction between the tyres and the road. Notice how, for each of these examples of circular motion, the speed is constant but the velocity is always changing. This is because velocity is a vector and has both magnitude and direction. Remember that a satellite is an object which orbits a more massive object. We've already looked at some natural satellites in this video. There are a couple of thousand artificial satellites in orbit around the Earth. These are used for things such as weather forecasting, communication, GPS systems and photography. This diagram shows the path of a satellite which is in a stable or fixed orbit around the Earth. At the moment, it's travelling at exactly the right speed for its orbital radius. This is the distance from the satellite to the centre of the Earth. If the satellite was to slow down, the gravitational force acting on it would cause its orbital radius to decrease. In other words, it would fall towards the Earth. If it slowed down too much, it would crash into the planet. If the speed of the satellite suddenly increased, the gravitational force acting on it wouldn't be strong enough to keep it within its current orbit, and its orbital radius would increase. If its speed became too high, it could travel right off into outer space. In your exam, you might be asked to work out the speed of a satellite such as this one, and the equation to use is of course speed equals distance divided by time. Here, the distance is just going to be the circumference of the circle, which is given by 2 pi r, where r is the orbital radius, and the time is the time for one complete orbit. Just in case you prefer it, here's the symbol version of this equation. Let's practice using this equation now with a couple of examples. In this first one, we can see that the satellite orbits the Earth once every 24 hours, and the orbital radius is 42,000 kilometers, so let's give it a go. The equation again is v equals 2 pi r divided by t, so subbing in that becomes 2 pi times 42,000 kilometers divided by 24 hours to give an answer of 10,996, or rounding up, 11,000 kilometers per hour. Example 2 is a bit different because here we've been given the time for one complete orbit and the orbital speed, and we need to show that the orbital radius of Venus from the Sun is about 110 million kilometers, so let's go. Starting off then with v equals 2 pi r divided by t, and subbing in that becomes 3 million equals 2 pi r over 225. Next, multiplying both sides by 225, we end up with this line. So in other words, 675 million equals 2 pi r. And so to find r, we just divide 675 million by 2 pi, which gives 107,429,586.6 kilometers, which is roughly equal to 110 million kilometers. That brings us to the end of this video on orbital motion. Hopefully all that talk of things spinning around hasn't put your head in a twist. To check, have a look through the exam style questions. Thanks for watching and good luck.